Welcome back to ECE 442-542. This is one class period after the exam, and I'll try to remember, if you'll remind me, to return those after class today. Exam number 2, not like we want to think about another exam, but that's essentially a month away. It's on the other side of spring break. That means don't get complacent, but I'm trying to let you know that really it's right after you come back from spring break that week. What was the average? That's always a question, and I tried to come prepared, and now do I remember. The average was 81 on the exam. Today what I want to do is spend a little bit more time on region of convergence, what it is, or give you the main patterns that you can be thinking about with this region of convergence. And those are really important when we're trying to get back from this transform expression, capital X of Z, back into the time domain. In order to obtain a unique time domain expression, we actually need to be given the region of convergence. We'll focus on that a fair amount in the next couple of lectures, but in this class, most of our experience will be based on systems that are causal, meaning systems that when you excite them, then they start responding. It's not like they're non-causal or they start exciting before you even excited them. But that's okay to have something that's maybe non-causal in a imaging or a signal processing application in a control. Usually we're dealing with you kick it, then it responds. More causal type behaviors, but it's nice to know what the distinction is or how you can now work with the region of convergence and how it then is incorporated into the inverse Z transform. And I want to give you the big picture today and mainly thinking about the main patterns that you can have when you are confronted with a region of convergence. This first, I guess that's 2 sentences. The region of convergence is determined independent of stability. So whether or not a waveform in the time domain or the signal is bounded doesn't depend on the region of convergence. I mean, it does, they're related, but they're independent of each other. However, a signal is bounded or a system is stable if its corresponding region of convergence contains the unit circle. You'll find that this region of convergence is some area in the Z-plane if the unit circle is actually on top of that region of convergence or is contained within the region of convergence, then the signal associated with that system is going to be stable. Yes, so the entire unit circle, the region of convergence will be a connected space. It's not going to be too disconnected, and we're going to have 3 main patterns, and that's what I want to start talking about now. But you'll never have, here's a fact that you can bank on. We've been doing a little banking in this class since we know now how to watch our bank account, and today maybe the investment would be wind power. Is that true? Anyway, I don't know, but it's pretty windy walking to class today. But a fact is that poles never lie on the region of convergence. They bound, or they're on the boundary of regions of convergence, but you'll never see, if you've now shaded in the region of convergence, you should never have X's in that shaded region. That's what I'm meaning by this fact. Let's now look at sort of what I'm classifying as 3 main patterns for these regions of convergence, and here is what I will designate as pattern number 1. And this coordinate axis is in the frequency domain, the z-plane, and here is the real part of z and the imaginary part of z, which I may or may not label consistently. Suppose that we now have a collection of poles, and I don't know why I drew them to be a challenge, but one of those better be the furthest away from the origin. And I'm going to assume that it's this one. And so this pole on the right is just inside. It's inside the boundary of this green circle, and the region of convergence, pattern 1, is exterior to all of these poles. Everything that's shaded is the region of convergence. And I'm going to call this region of convergence unbounded region of convergence with a central void. The center has been cut out of this z-plane. That's my central void. What's not in that dashed circle is not part of the unit of the region of convergence. Nowhere have I indicated a unit circle on this z-plane. That's why this drawing is independent of stability, because I haven't yet indicated anything about the unit circle. But is it clear that the region of convergence is going off to infinity by this diagram? That's what I'm meaning by unbounded. That's in the z-plane. So this is the region of convergence includes infinity. Yes. So the question was, where's the region of convergence relative to that dashed line? And it depends on the accuracy of that dashed line. If the dashed line is drawn at the same radius as that pole, then the region of convergence would be just beyond that dashed line. If the dashed line kisses that pole or doesn't yet touch it, then the dashed line is part of the region of convergence. So the region of convergence is outside of all poles. Is that? I never know quite how to explain that, but it's not, a pole is not on the region of convergence. So here's my description. And I may have two different ways, and so I'm saying pattern 1, phrase A, the region of convergence lies beyond all poles, or pattern 1, phrase B, and these are supposed to be equivalent descriptors. All poles are interior to the region of convergence. Whichever phrase makes the most sense to you, or if you can come up with a better one, as long as it's consistent, then we should be okay. Now, what we would like to do is try to determine, based on this pattern, what our time domain sequence of numbers looks like. This region of convergence is this pattern, but right now it's determining or any value of z in the region of convergence keeps capital X of z bounded, or that's when capital X of z converges, is any point z belonging to that region of convergence. And what is our z transform expression? It's from minus infinity to infinity of this time sequence, little x of n, z to the minus n. That's how we've defined the z transform, which if we just started putting down the infinite number of terms in this series, we would have, coming up from the left, x of minus 2, z to the minus minus 2, which is z squared, plus x at time or at instant little n minus 1, z to the minus minus 1, which is z to the 1, plus x of 0, z to the 0, plus x at time 1, z to the minus 1, plus x of time 2, z to the minus 2, etc. So that's the general structure from the definition of our z transform. Now, based on what we see for this region of convergence, can you tell me anything about certain values of this sequence? Let's say x of minus 2, x of minus 1, x of 0, x of 1, x of 2. And what I'm getting at is look at some limiting conditions on that region of convergence. This region of convergence, I said, goes unbounded. A value of z, then, living in that region of convergence could go all the way to infinity. So there's one of our extreme cases. If you now plugged in z going off to infinity in these terms, and remember, the region of convergence is supposed to be bounded for values of z in the region of convergence, do you see certain of these two terms actually cannot exist? If you plugged in or let z go to infinity here, let's say for x of 2, that's now x of 2 divided by z squared. Letting z go to infinity, is that well behaved? That term. Now z's downstairs, so letting it get big just shrinks that particular contribution. That's okay. But now if we go back to x of minus 2, that's now multiplied by z squared. And what did we just say? Z in this region of convergence for pattern 1, it's allowed to go big, really big. What would that do to capital X of z? Would x of z remain bounded for that choice of z? No, so that essentially forces this term to 0, does it not? What about this term? It's scaled by z, and z, we said, in this particular pattern for our region of convergence could go to infinity, and it also has to be 0. Do you see what's happening to the left on all of these terms for this unbounded region of convergence? That's forcing all of those elements in that sequence, or those sequence values, x of minus 2, x of minus 3, x of minus 4, those are forced to be 0. The implication that you can take away from this particular pattern, pattern 1, that's outside of all poles and going unbounded, is that your sequence in time, the implication then is that x of n is causal. meaning x of n, or another way of saying it would be x of n is equal to 0 for all n less than 0. Pictorially, you now have x of n that takes on only non-zero values for non-negative integers little n with this particular pattern of region of convergence. That's pattern number one, an unbounded or a unbounded region in the z-plane with a central void, and inside that void are all of your poles. Now you're probably wishing you were back in art class, right? Now we're drawing. That was pattern one. Pattern two. Yes?
So, like, what about the void? The central void, is that, so it's not merging there?
So now what about the central void? The region of convergence is not in there. There's no z's in that central void. So you can't, for values in there, capital X of z will not converge.
Is there like an argument for that, like similar to what you just did for the negative value, causal stuff?
Well, if you look at a time sequence that's causal, and you plug it into this formula for capital X of z, that's how we've actually found these limits. We know that this magnitude of something times z to the minus 1, that magnitude has to be less than 1. And that tells us that the magnitude of z is beyond all of our poles. And that's what's creating that central void. You'll start to, I hope, make this connection stronger, but here I'm giving you the big picture, and I'm trying to give you the different patterns to keep in mind. Pattern number two. And this is a coordinate system. What's that coordinate system did I say we were worrying about today? That's our z-plane, not the s-plane. This is another complex plane. This is the z-plane associated with discrete time sequences. Now what I want to do is put a few poles here. And my region of convergence now is inside the pole closest to the origin. This is really the complement of the previous pattern. Now instead of having a void, now my region of convergence is that little disk in the complex z-plane that's bounded by the pole that has the shortest radius from the origin, or the smallest. This particular pattern, then, I'm saying is a bounded disk, ROC. Pattern 2, description A. The region of convergence lies inside all poles. Yes. Pardon? Including, pardon? What was the fact? that I said earlier. Where are the poles relative to our region of convergence? They're never in the region of convergence. Is everybody clear on the fact? Only the facts. No, we have more than facts sometimes in here, but that fact keep in mind when we're talking about region of convergence. The region of convergence never contains poles. So that's one, is the region of convergence is inside all the poles, or another way to try to say that is all poles are exterior to the region of convergence. And now let's see if we can what the implication is for this pattern. And we want to maybe compare that and contrast that with the implication from pattern 1. And if you forget which is which, just remember the definition of the Z-transform. That you should have memorized until after the final exam, in this class at least. And you might want to have it memorized if you go on an interview. It might be helpful, who knows. But this is not that hard to remember, I hope, at this point. Now we simply expand that out. And what are we looking for now? Well, now we want to find maybe an extreme value of Z that forces certain values of your sequence to vanish or to equal 0. Let's go back to our region of, because the region of convergence, any point, any Z value in that region of convergence should allow capital X of Z to be bounded or well behaved or to converge. Yes?
So both exist both in the unit circle and outside the unit circle, where there will be a region of convergence.
So now the question was, if the unit circle is, I think you said something like, if this was the unit circle, I don't know why I drew that. I don't want to erase it because it's going to be tedious to erase probably. But let's say that red hashed is the unit circle. Now I have some poles that are inside the unit circle, some poles that are outside. Forget that for now. That's not what we're worrying about. We're just finding the region of convergence. So these are independent relationships. We can have a region of convergence whether our poles are inside, outside, or anywhere relative to the unit circle. Meaning, let's forget, that's why I'm not right now commenting on this red dashed circle. It's unimportant to what we're trying to figure out right now. We're not talking about stability, we're just talking about whether it's a causal sequence, an anti-causal sequence, or a two-sided sequence in the time domain. Now, what's an extreme point or value of Z in this region of convergence? 0. That might be, that's the other side of these extremes. The one was way out there at infinity. Now an extreme is right there at the center. So if Z is equal to 0 is in this region of convergence, does that cause some of these terms, does it force some of these terms to actually go unbounded if the sequence value was non-zero? It does, doesn't it? Because now look at the positive values of index n. This is now x of 1 over z. And if we let z go to 0, that's going to go unbounded. This now pattern is saying that this sequence value is 0. Likewise for this one. Likewise for all of those that are to the right, or for positive indices. In this case, I'm going to go ahead and, well, let me state the implication. The implication is that x of n is non-causal, or x of n is equal to 0 for all n greater than 0. And typically I will actually just associate n equal to 0 with the causal piece, but you can see that that constant is not going to cause this to go unbounded by letting z equal 0. So x of 0 could really be on any of these two sequences. Is that clear? And we'll broaden this later, but for now, let's just sort of agree that non-causal means little n is negative. But in fact, it can equal 0, and you could still sort of say that that's non-causal, but you want to kick it, and it actually shakes before you kick it. That's really non-causal. So it should have been shaking, and then you kick it. Was there a question?
I was just confused. So x of n is, so the reason for this x of n can go anywhere except 0 if you want x of n the value of the.
So little x of n's are the sequence in time, and capital X of z is its corresponding frequency domain z transform. Capital X of z now is looking at weighting these sequences with powers of z. And it gives us now, it's condensing all of this time domain history into a new quantity that's going to be a transform in the z variable, the complex variable z. And in that case, then, these little, or the little x's, the lowercase x's, are the time sequences. And we're simply scaling them in this case. If we had this pattern, pattern number 2, then that, when we have a bounded disk for our region of convergence, that's actually implying that whatever sequence we have based on these poles is defined when n is less than 0. So now we would have x of n being x of minus 1, x of minus 2, x of minus 3. That's the sequence that we would be seeing for this particular region of convergence pattern. Or, if that's the description, the picture would be like this. Here is the x of n for pattern number 2. Minus 1, minus 2. Here is n. And it just keeps going. Or it can. It's unbounded in the negative index direction, in the time index. That's our sequence. And that would then give rise to pattern number 2. Pattern number 3, or main general pattern. And so far I haven't really said anything about whether these sequences are bounded or not in the time domain. So what I mean by a bounded region of convergence, don't confuse that with a sequence that's unbounded or bounded. Bounded region of convergence means that it's some finite area. Unbounded means it's going off to infinity in the z-plane, in the complex z-plane. That has not yet been connected with the time domain sequence's behavior. Pattern number 3. Z-plane, still. And now let me Did anyone go out over the weekend and buy some dividers? How about a compass? I need a compass now, don't I? But that's supposed to be two circles. The inner circle is supposed to be enclosing all of those poles, and the outer circle is supposed to be interior to this pole on the left, and the region of convergence, now we're back to a food theme. This is a donut shaped, it's annular, it's a bagel shape. This is our region of convergence. Yes?
Did this ever happen outside of like some kind of composite system that's like a system? More than one system?
So this can be, this particular pattern, maybe you're already there ahead of me, but this pattern now corresponds to a two-sided sequence. It can be infinite in extent in the negative direction and infinite extent in the positive direction. So for little x of minus n all the way to minus infinity, little x of n all the way to plus infinity. So this is a never-ending signal. You could think of it as a sinusoid that is always on, always been on, never will finish. That's corresponding to this. So, this pattern, pattern 3, is, I will say this is an annular or donut-shaped region. Whether you can believe it or not, none of these poles are on top of the region of convergence. They can't be. That's the way the region of convergence works. So one description 3A, is the region of convergence is annular or donut-shaped, or 3B, some poles are interior to the region of convergence, and some poles are exterior to the region of convergence. Yes?
Wouldn't all poles be both interior and exterior? Which point of view, like which piece would it interior?
So now I'm not quite, see, I never know how to phrase this, but there should be, I hope, some poles inside, sort of a void, and then the region of convergence, and then the other poles are in sort of another void that's outside of that donut. And you can hopefully see that this region of convergence is connected, meaning you can get from here to there while staying in the region of convergence. Likewise, this region of convergence is connected. You don't have to exit the region of convergence to get from red dot 1 to red dot 2. And likewise in this pattern, pattern number 1, you can go from there to there, always staying in the region of convergence. So the region of convergence is a connected region in the complex Z-plane.
So does that only happen when you have like a system that has like one component that's like the causal and another component that's the
It's easier to think about something non-causal and causal when you think of a signal and maybe not a system. So in this particular class, you can have signals and you can have systems. You could have a capital X of Z that corresponded to a signal, or you could have a capital X of Z that corresponded to a system's transfer function, so to speak. But it's probably easier to think about signals having this infinite expanse in both the negative time and the positive time, and not so much a system. But a system you could think of in terms of maybe image processing. You now may be filtering, and you may have to have it somewhat anti-causal in behavior. So think of the sort of the sync function as its impulse response, which is essentially saying, I don't know how, but it somehow knew, it anticipated that I was going to ring it at time 0, and it was already starting to build up before it got there. And if you had the ability to delay your processing, you could sort of anticipate having something that was anti-causal in terms of a signal. I'm sorry, in terms of a system. Question?
So when you say that you can get from the red dot to the other red dot, that's not just a straight line?
It's not a straight line, so you're able to go like this. And I shouldn't be doing this. Now somebody will see these notes and they'll go, what's that wave that's passing through the region of convergence? So I will eliminate that right now, but you don't have to connect those dots with a straight line. You just have to stay within the region of convergence. Where was I? A connected space in the z-plane, and here the implication for this pattern 3, which I've already been discussing, is that it's two-sided. The sequence, little x of n, is a two-sided sequence. Or the sequence, little x of n, is non-zero for n greater than or equal to 0 and n less than 0. Meaning now that two-sided, or that region of convergence, that donut region of convergence, is connected with this time domain sequence, where the time domain sequence came up from negative time and continues for all positive indices. Those are the three main patterns. Pattern 1, a central void and an unbounded region of convergence. That was what kind of a time sequence was associated with that region of convergence? Causal. Then its complement, where we just had the disk. What time sequence was associated with the region of convergence that was inside all of the poles? That was when we had negative indices, or an anti-causal sequence. And then finally, when we had the donut, we had poles inside and poles outside that region of convergence. That's we had a two-sided time domain sequence. Now what I want to do is just completely mess with your thinking. It's not intentional, but we have to think a little bit about some variations on those three main patterns. But those are the three main patterns to try to keep in mind. Let's look at some variations. And I'll say this is modified pattern number 1. Do we remember what pattern number 1 was? And now you have to remind me, because this was a long weekend. Okay? Didn't get the sleep maybe that I should have. What was pattern 1? Pardon? Okay, it was unbounded, wasn't it? So it was something like this. But you know what I want to do with this modification? I want the pattern to be outside all my poles, but now I don't want it to go to infinity. I want it to be bounded in extent. I don't know how to do that, so I'm going to just say, let's agree that this box keeps the region of convergence less than infinity. It's going way out there, but we still restrict it from going all the way to infinity. She's back. Last year, every time at this time, we had a pound, pound, pound. She's posting posters outside. I caught her one time. I went around because I was curious, what is happening at whatever time? Because every time it was poo, 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 and I thought, who is causing so much racket? I think I need to just remind them that there's a class going on here. For those of you at home, you probably don't know what's going on, but if you want, you can stand up and hit your wall. It'll be the same effect that we have right now. But here, we have modified pattern 1. And what I'm trying to do here is I'm wanting to say, what if Z is not allowed to zip off to infinity? Or, now the region of convergence, let me call this distance. This is supposed to be a circle. It's not supposed to be an oval or an egg or anything. This is supposed to be symmetric with respect to the origin. Let's say that that radius out to the furthest pole is r sub 1. And now what I'm saying is the region of convergence is bounded at the bottom by R1, but it's also bounded away from infinity. Or another way of saying it is that the region of convergence remains bounded. Yes?
That just means that like the accent has like some like negligible like non-causal.
Yes, exactly. So you guys are way ahead of me. You're getting sense beaten into you by that person out there. I'm just hearing it as an annoyance. But yes, did everyone hear what that comment was? What does this really mean? Well, what was the original region 1 pattern, or pattern 1? What did it correspond to? What sequence in the time domain? When was the sequence present? What values of little n? Positive or non-negative, right? Now with this particular pattern, without going all the way to infinity, we actually can go over into the left, into the negative, and pick up a finite number of sequence values. We can now go to minus 106 for n, minus 462, and then we can keep going all the way to n equal 1,000, n equal 168 million, etc., and just keep going in the positive direction. So you might hear this, referred to as little x sub 1 of n is right-sided, meaning it goes off to infinity toward in the right, but it can actually start before that line in the sand that we've labeled as little n equal to 0. You see why this is a modified version of the first pattern in the z-plane, or pictorially, now we can go back here to, let's say, minus m. M is finite. We're not infinite in extent to the left. We're starting at a fixed finite value, and then we keep going to the right. The time sequence, little x sub 1 of n, is allowed to be non-negative for all values of n greater than or equal to minus capital M, and here minus m is negative. But I hope that you can see why we didn't start with this description. This would have been kind of confusing, I think. So starting with the generic patterns, 3 patterns, and what's this one different? How is this different? We just don't go all the way to infinity. Run, Forrest, run. Forrest doesn't have to run all the way to infinity on this one. He can actually stop. I don't know, I was going to the right. Oh, this is, never mind. Your right is different than mine. Questions on this? Modified pattern 1. Now we've picked up a little negative indices. Yes?
How do you choose M? Like, is that just
M is going to be dependent on, how do you choose capital M? That's going to be dependent on your sequence. And we'll go through some examples in a minute. Okay? I hope. If we get through all these modified patterns. Luckily, we just had 3 patterns, right? And I think we're going to only modify 2. Because I can't modify a donut other than eat it. And then it doesn't stay symmetric, and it has to be symmetric. Gosh, I guess it's that time, yes. So, modified pattern number 2. Pattern 2 was a bounded disk. What was the extreme case here? 0. So now what are we thinking we're going to do with this modified pattern? We're going to take something, a hole punch, and remove the origin. And the way that I'm going to do it, because I don't want you to confuse this with a 0, my removal of this is like we removed infinity. I'm going to remove this with a square. That's just removing z equal to 0. That's the modified region of convergence. So in effect, I have to remove this line. I can't have the origin in my region of convergence. So now, what if the region of convergence doesn't include z equals 0? i.e. the region of convergence, or is defined by having the magnitude of z strictly bigger than 0 and less than, let's say, r sub 2, where this radius is now r sub 2. X sub 2 of n is now left-sided, meaning we can go and pick up a few sequence values in the positive time index little n. X of n is left-sided, not just anti-causal. So that now we could start up here at n, and then go off to the left. Where x sub 2 of n is non-zero for n less than or equal to capital N. Again, n, capital N, is positive. Question? Pardon? You guys are great. So the next part of this presentation is going to be a finite sequence. Finite on the right and finite on the left. Okay? So that's where we're headed. Yes?
What's the difference between those last two and annular? Like, is it just because they're really close to 0?
Who can answer that question? What's the difference between modified pattern 1, modified pattern 2, and annular? Answer.
Modified pattern, or annular is between the between some equals, whereas modified pattern 1 is outside all of them, modified pattern 2 is inside of all of them.
So the region of convergences are different. The one is annular. The other one is basically unbounded but bounded, if that makes it. It's outside of a void. The second pattern is a disk, and then we have the origin punched. But now the difference is these only allow a finite number. In the time domain, the difference is these only allow a finite number to the left or to the right. The annular allows for infinite extent in both the left direction and the right direction in time. Question?
Yeah, so for the modified pattern, are we putting out everything inside or outside of a given ring of a finite radius, or are we putting out only 0 and only actual infinite value?
So we are only cutting out the origin in pattern 2, z equals 0, that's removed, and in pattern 1, the modified pattern 1, we're only quitting the opportunity to zip off to infinity. So we can go as big as we want, just never go unbounded. Okay, we can go and go and go, and you just define how big you want to go. But it can't go to infinity. Now, I think maybe we just have to have student presentations because that's what's happening next. Now we want to do is, what if x sub 3 has finite duration? What if, is it clear that the last two, x sub 1 of n, was infinite in duration? It had a interval of time, little n, that was infinite in extent. X sub 2 was infinite in duration to the left. I guess I should be doing this. And x sub 3 is going to be limited and only finite, either to the left or the right, or both. X sub 3, what if x sub 3 of n has finite something's going off to infinity in the wrong direction on me. So let's see what happens when okay, sometimes that forebodes something I don't care to have happen. Hopefully we'll still be okay. But what if x sub 3 of n has finite duration? Or x sub 3 of n is non-zero for n living between two finite bounds, minus m and n. In this case, what's the region of convergence? Then the region of convergence can include all of the complex plane except two different cases. A, region of convergence doesn't go off to infinity. If x sub n, 3 of n is not equal to 0 for n less than 0, and or B, so you could have both of these, region of convergence doesn't include z equals 0 if x sub 3 of n is not equal to 0 for n greater than 0. Yes? I don't know. Interpret at your peril. The question was, which of these are supposed to be met or not? So as I was writing those, I'm not sure that they made that much sense to me. So let's see if we can clean these up. Or let's just go through some examples and see if that clarifies. Okay? So let's look at some examples without trying to get bogged down into this. But essentially, you could have a finite sequence that only had negative indices. You could have a finite sequence that only had positive indices, or you could have a finite sequence split between, or split on either side of the origin. And one or both of these will be in play in various cases. So let's look at some examples. First, suppose, I think we're up to sequence 4, x sub 4 of n is 5 delta of n plus 6 delta of n minus 1 plus 7 delta of n minus 2. Suppose that is x sub 4 of n. Just so that we're all on the same page, what does that look like if we had to sketch that sequence in time? And those deltas are impulse, discrete time impulse waveforms, which have to be on when their argument is 0. That's what I'm meaning by that.
5 delta x delta 1.
This is only going to be on at 0, 1, and 2. Is that? It's going to be 5 here. It's going to be 6 here. And it's going to be 7 there. Is that true? Pardon? I don't care. They're delta functions. Delta of n. Okay? In the time domain, they have amplitude of 1. So it's not as critical. And I'm sorry, in discrete time, it's not as critical. So now, let's look at what's the z transform of this. And if you couldn't quite remember, you could just plug in the definition, right? You could say, well, this is something happening at all of these, or each of these numbers are only existing at one point in time. And where does that 5 exist? When little n is equal to 0. So that now capital X of z, if we looked at this, the sum from n equal minus infinity to infinity of x sub 4 of n, z to the minus n, do you see that we would have 5 times z to the 0 plus 6 times z to the minus 1 plus 7 z to the minus 2. That's the z transform. Or if you wanted to, you could say that's 5 plus 6 over z plus 7 over z. And when is x capital 7 over z squared? Thank you. So now, where is capital X sub 4 of z bounded? For what values of z? What's the region of convergence for this sequence? This sequence, is everybody clear that this is a finite sequence? It's only defined, it's non-zero over a finite interval or a finite duration of little n's. What else do we know about x sub 4 of z? Where is it well behaved? Where is it bounded? Where does it converge? Capital X sub 4 of z. For what values of z? Pardon? Anything that's not equal to 0. It's the entire complex plane except we punch out that 0, z equals 0 value. And what was this finite sequence? It was finite to the positive side. And so it said, oh, we can't have, so here the region of convergence, I don't know if this is going to be very clear, but here our region of convergence is the entire complex plane minus the origin. Is that, pardon? So now, is infinity a possible value for capital X sub 4 of z's region of convergence? Is z going off to infinity allowed in this region of convergence? If you let z go to infinity, is x sub 4 of z well behaved? It's going to just be in the bottom and it's going to get big, isn't it? But what happens when you get big in the bottom? You shrink. So it's okay, isn't it, to go off to infinity. Z can go off to infinity. But it can't be right at z equals 0, can it? Then it's unbounded. So we have the entire complex plane except the origin. Pardon? I'm hearing things now. I'm hearing voices. I was hearing knocks before. Let's look at another example. 2. Suppose x sub 5 of n is 4 delta of n plus 1 minus 7 delta of n plus 2 minus delta of n plus 3. Can you draw this? Capital, or I'm sorry, lowercase x sub 5 of n.
I just had a quick question about the previous example. So like before we were talking about negative positive n values, and now you're talking about the ROC in terms of z. So like how?
So the region of convergence really hasn't changed any that I'm aware of. Now capital M and little n are the same. They're still bounded. In this last example, what was capital M? You could say 0 or it's not important, right? It doesn't exist. Capital N is 2. Is that okay? But capital N is just a bound on the time index little n. And that means for this finite duration, usually when you have a finite duration time sequence, you have the entire complex z-plane allowed for the region of convergence, except for two possible extremes, the origin and or infinity. In the last one, we had finite to the right in the time, and infinity was allowed, but 0 was not. Now what? What does this look like, and what would you expect to have happen here? Well, if I eliminate it, or what's this sequence look like? Where is it non-zero? Infinite in extent? So you're way ahead of me. I'm still trying to draw. I was back in art class. Here's minus 1. But there's the time domain sequence. And we can now z-transform that. Capital X, which one are we on? 5 of z. You could go through the definition and find when are these non-zero, but we now have 4 z to the minus minus 1, or 4z, minus 7 z squared minus z cubed. And what's this region of convergence? As long as z remains bounded, we're okay. Here, region of convergence 5 doesn't include infinity, and or region of convergence 5 remains bounded. So it's all of the z-plane except infinity. It's C except for the unlimited case. Origin is okay. If you plug in z equal to 0, is capital X sub z of 5 okay? It's fine, isn't it? It just equals 0, but it's well behaved. Question? So now, what happened to our poles? Where are they at? Well, in this case, we don't have any. Well, we have poles, but where are they? In capital X sub 5 of z. They're at infinity. We really prefer bounded poles. We don't have a ratio of polynomials of z. Here, where were your poles? At 0, if you wanted to view them that way, but I would probably say let's not even bother with worrying about poles. We have all of our complex plane, and then we can live with our poles not being in the region of convergence if we don't worry about poles in these finite cases. One more. And suppose x sub 6 of n is equal to 2 delta of n plus 1 minus 4 delta of n minus 1. What's capital X sub 6 of z? What's the z transform of this? Is that what I heard? So 2z minus 4z to the minus 1. And what is our region of convergence here? It's now away from the origin and bounded. The entire complex plane except for those two limiting conditions, or RO region of convergence 6 doesn't include z equals 0 and doesn't include infinity. And now, hopefully, with those examples, you can sort of go back and clean up the verbiage that was before when we were talking about a sequence being, wherever it was, non-zero for particular values of n, and it depends on whether they're right-sided or if they have some signal in the negative index or in the positive index or in both. But that's now our region of convergence, big picture. How many patterns did we talk about, main patterns? 3. We had one that was void in the center and unbounded. We had its complement, which was a disk. And what did the time sequence look like for the disk? It was anti-causal, wasn't it? And then we had the donut, or the annular. So we'll start next time with a quiz. How's that? And because we're finishing up early, you have to pay the price somehow. So we'll start with a quiz next